Okay, so remember last class we were looking at fuel for cement, right? And if you remember, we looked at two fuel. For example, one of them is a pet coke, right? Pet coke, and another is a heavy fuel, for example. Now, carbon is 97% and rest all materials are there. In this one, it is around 86.6%. Now, finally, the heating value is 33.2 megajoules per kg, and this is 39.5 megajoules per kg, because this hydrogen must be contributing, okay, whatever it is. So, the consumption kg per kg of clinker is 0.096 and this is 0.142, kg per kg of clinker, right. So, if I look at it, I can actually calculate out, because it will be 0.142 multiplied by 39.5, because this is the amount of fuel consumed per kg of cement, and this is the calorific value. So, this is the megajoules used up for per kg of cement, megajoule used up for per kg of cement, right. So, the embodied energy, if somebody is trying to calculate out right from the all ingredients and things like that, one can actually get some idea, or how much is the energy actually used for clinkerization of cement. So, something like 0.39, let us say 40 into 14, 140 into 40 into, let us say 40 into 142, that would be megajoules per ton, because 0.142 was there multiplied by 1000. So, 40 into 142 megajoules per ton actually, or if I am trying to find out for per kg, this will be simply like this, which will be how much, something like 56 point something, yeah, megajoules, right, per kg of cement. So, that is the energy consumed for clinkerization anyway. So, that is right. So, this I already mentioned in the last class, the amount of heat released when heating value is, that is how we define, and we have two of them, high heating value, higher heating value, and the lower heating value. In this one we are assuming everything, it generates the heat and then everything is in the original state. For example, there will be some moisture which will vaporize. So, latent heat is absorbed by the moisture vapor. Now, if it comes back to the water state, then the heating value that you get, because then all the heats are released and it would have gone for clinkerization process. So, higher heating value corresponds to no water moisture vapor, this also at the state of water as it was combined in the fuel itself, because that's why it's higher. Lower means water has gone as vapor, therefore, that heat is not available for using for clinkerization or whatever it is. So, that is what the fuels are. So, that is what the additional fuels, lot of fuel, people are trying to use a lot of them, like waste tires, biomass, used solvents and sewage sludge, municipal solid waste, other waste, and in all these cases, you get an advantage, because these are waste material, you would not have used it otherwise. So, in accounting, this will not go to my carbon accounting actually, because this was already there, waste material, I do not know, I would have had to have some bioproductive land for depositing them or doing something, right. So, these ones do not go into really accounting. So, this is an advantage from environmental point of view, both accounting point of view, otherwise also because you are reducing down the waste generation, because all kind of if you see many cement plants during the in the preheater, they used all kind of waste materials. And these calculations we have done already, that the amount of carbon dioxide generated, right, and from the fuel, because we said 100 to 200, not 2200 kg of coal for 1 ton of clinker if you are using coal, and that gives you around points. So, these calculations I think we looked before earlier, and we said that is why we say, because this is from stoichiometric relationship. Supposing I have got 65% calcium oxide in my Portland cement, then for 100 calcium carbonate 56 kg of 56 kg is the calcium oxide, 40 is the carbon dioxide, right. So, 65 by 56 is I have to use 1.16 tons of calcium carbonate for in 1 ton of cement, right. 1.16 tons of calcium carbonate will go in 1 ton of cement, right. So, this produces this, if you look at it, 65 by 56 into 44 by 100. So, it gives you about 51 ton, because from 65 in 100 kg or 100 ton or 1 ton, you will have 0.65 calcium oxide. Corresponding to 0.65 calcium oxide, this divided by 56 will give you how much calcium carbonate is required, and from that much amount of calcium carbonate you produce 40 40 by 100, 44 carbon dioxide. So, therefore, this is the carbon dioxide that you produce from 1 ton of cement because of clinkerization. But fuel also produces carbon dioxide, and this is because if you use 44, because you are assuming if it is all carbon. So, 1 carbon produces CO2. So, carbon 12 produces 44 carbon dioxide, 44 carbon dioxide. One because 12 mass of carbon will produce 44 mass of units of mass of carbon dioxide. So, 44 divided by 12, and if you are using 0.1 ton, that is 100 kg, or in the extreme case 0.2 tons, this is 0.2 tons, then this will be 0.37, 44 by 12 into 0.2 or 44 by 12 into 0.1. So, 0.37 to 0.74. That is why we were saying that my total carbon emission for 1 ton of cement will be 0.51 plus 0.34, which will make it 0.75, or 0.51 plus how much was it, double of it actually, 37, this was 37. So, 37 means 78, and this was 74. So, how much this will make it? 1.25. So, on an average, if you look at it, I can say that 1 ton of cement produces 1 ton of carbon dioxide. So, that is the issue actually, and that means you would need more carbon land for sequestration of this carbon. To have this carbon, you need more plants to absorb this carbon dioxide, and that is why if you produce, so this is a contribution to carbon land and ecological footprint. So, that is why people are so much bothered about the carbon issue in cement, other than of course fossil fuel, very much it is there. And we know of course the greenhouse gas effect emission from, of course, other gas, the relative emission from cement is 800. So, if I take this is the emission relative damage index 1 to this is 15,000, but emission from cement is something like 800, we have seen earlier in a table. So, NOx from cement is around 1 to 9 kg per ton from fuel, because nitrogen get oxidized to nitrous oxide at that high temperature and something of this kind, right. So, that is what it is, and that is what we have seen that carbon, this is a kind of Joules per molecule. I think I will not look into this, the chemical exergy part, this is not important right now. I am looking at that, right, this I am not looking at, and heating values, that is what I was interested in. Heating values I am interested in. Okay. Now, this in case of process, one is interested in the exergy part of it, where we find out you even remove out the entropy losses, because wherever you are producing, you are converting energy into work or something, there will be some energetic efficiencies there. From this much energy you produce the work, but there is some work efficiency, as I showed in case of coal, because you are bringing down from the mines to finally when you are producing the high power, there is a lot of losses every state. So, carbon dioxide, you see, now you have produced calcium carbonate is a natural material, it is stable. Calcium carbonate is stable, magnesium carbonate, these are carbonates are stable. Calcium oxide is not stable, the moment you bring in contact with water, it will form calcium hydroxide, and if you leave it to the atmosphere, it will then convert it into calcium carbonate. because calcium oxide plus water will lead to calcium hydroxide, and this in added to carbon dioxide will form calcium carbonate. So, final stable state is this. So, you give energy to convert calcium carbonate into calcium oxide in the cement, and therefore, it will have always a tendency to go back. So, hydration reaction, you add water to cement, for when you add water to cement, we know that tricalcium silicate, which we call C3S, then dicalcium silicate, which we call C2S. This when reacts with water, you can actually have the X and Y or whatever it is, it produces some amount of calcium hydroxide, which you denote as calcium hydroxide with oxide and water, something like this. So, you write it as CH. In this abbreviated form, we write calcium hydroxide as CH, right. It produces some CH plus calcium silicate hydrate, calcium silicate hydrates as we call it. This would be CHS here. So, this calcium hydroxide is produced. So, calcium straight in the cement reaction, I get calcium hydroxide, and in the long run calcium hydroxide absorbs carbon dioxide from atmosphere in presence of moisture and goes back to calcium carbonate state, and that in concrete technology we call it carbonation process, which reduces down pH, etc., but that is not the issue here. Issue is that cement in the long run, 1000 years or millions of years, cement hydrates will again tend to, some of it will tend to go back to calcium carbonate from where it has come, right. Let us see what happens actually. So, this is carbon dioxide from concrete 3 billion tons, 10% is absorbed back as carbonation immediately, after some time, over a short period of time. In 2009, it was world produced 3 billion tons, and 10%, because as I said, calcium hydroxide in the cement will absorb carbon dioxide in presence of course water and form this. Now, not only that, in this will make our this will make this system makes, when I have reduced down my calcium hydroxide, the CSH, as I said, that is your calcium oxide SiO2 H2O, some X, Y, Z, right. This will be the calcium silicate hydrates. Now, this itself is not stable at low pH, not stable at low pH, stable at low pH. So, even this, when calcium hydroxide is consumed by carbon dioxide from atmosphere through carbonation process, even this is not stable. This tends to get converted into carbonates. So, that is the reaction. So, that is the reaction, you see. So, this is the calcium silicate, carbon dioxide and water, and it will form calcium silicate of this kind, calcium carbonate. So, directly also calcium silicate, tricalcium silicate reacts with carbon dioxide to form calcium carbonate and of course, silicate hydrates. And besides that, in the long run, all of them can get converted into calcium carbonate back, but it will take very, very long time, very long time, because it starts the reaction process, physical process is also involved. The carbon dioxide must reach to the cement hydrates, and at the surface it can reach, surface is exposed to carbon dioxide, but to penetrate into inside, carbonation front must penetrate inside, and if all the concretes are to be getting, they should be carbonated and CHS are to be broken to calcium carbonate, it will take very, very long time, right. So, therefore, 10% absorption one can take globally for the whole year, different ones which were constructed earlier, etc., etc. So, some carbon sequestration occurs, and this reaction process involves diffusion of carbon dioxide, and there are several intermediate steps. So, philosophically we can understand, it has come from calcium carbonate, it will go back to the, it will again go back to the calcium carbonate state, which is stable, but it will take very long time, millions of years maybe, if everything has to be carbonated. Okay. So, this is the, therefore, this is the carbon issue of cement is important. So, people have been trying to actually work with various other types of cement, right. This is one issue. So, since so far we are looking at cement, and relative issue related to cement we are looking at, we will go to concrete later on. So, if you look at cement of the other kind, there are varieties of cement that has been actually attempted. You must be familiar with something called Portland pozzolana cement. Portland pozzolana cement. This is PPC, Portland pozzolana cement. For those who are not familiar with concrete technology so much, I will just we will talk about this also. This is Portland slag cement. These are very well known cements. Then silica fume has also been used, metakaolin, these are added to the cement system, rice husk ash and limestone powder, right. Various other kind of ashes, sulfur concrete, there are some other types of cement has been tried like high baelite cement, I will come to all of them, reactive magnesia cement, and then nanotechnology based modifications. These are attempt made to reduce down the carbon dioxide production from cement, because ordinary Portland cement if you have, you will have 1 ton producing nearly 1 ton of carbon dioxide. So, if you can add something, dilute it with something else one way, and there are newer types of cements, or not newer, there are many of them are old, but they have been now re-looked into. Alkali activated cement system. So, we will look into each one of them. Now, if you want to look into this, then first we must understand we are dealing with lime system, right. We are dealing with lime and silica system. So, lime has been there cementing material for long back, right, and currently also people use it for archaeological restoration of monuments, archaeological monuments. There are 2 types of lime, hydraulic and non-hydraulic lime. So, non-hydraulic lime sets when excess water evaporates and calcium hydroxide. So, what you do is you take the limestone, produce the lime, it might have more quantity of calcium oxide which with water will react form slagged limes, calcium hydroxide, and when exposed to atmosphere absorbs carbon dioxide to form calcium carbonate, therefore, it solidifies. So, use of lime is very old, right. In fact, it is recorded is that first use was possibly in Israel somewhere, they did the recording. It might have been elsewhere, but they found out, traced it out somewhere around 8000 BC. So, nearly around 10,000 years you are using lime, right. Hydraulic lime is the other one which contains some active clay, because clay will be the impurity in lime as well. So, it contains some active clay. So, as you add water, clay reacts with the silica reacts with the lime, but this process is relatively slow. As long as your clay is reactive, clay would mean silica and alumina, and if it is reactive, then if it is reactive, not all clay or silicas are reactive. For example, quartz is not reactive, quartz is crystalline, very stable material. You have silica all over the place and they are in the nature, therefore, they are not, they are stable, they would not react further, right. You see, man-made materials are not stable, natural materials are stable, because man-made material would be produced with the expense of energy. So, you raise what is called chemical potential, it will have a tendency to react. So, clay, all clay are not reactive, reactive ones would react. So, some clays are reactive, and how they do become reactive, let us see a little bit. Okay. So, this is pozzolan's name came from volcanic ash. Now, volcanic ash is the ash that comes out in the volcanic eruption in the beginning. So, what would have happened actually, the clay would have subjected to a lot of heat, right, hot powdery like thing ash, and this would settle to the atmosphere. That means around 25-30 degrees centigrade, suddenly it is exposed to 25-30 degrees centigrade. So, clay heated and cooled rapidly. Volcanic eruption. So, that clay again, because you have heated it up, silica and alumina system, and cooled it rapidly, that means certain amount of energy would be trapped in that. It will not form, it will not dissipate all its energy which has gone in heating, and it would, it would be then, therefore, its chemical potential is increased. It will have a reacting tendency. So, that would give rise to reactive silica and alumina system, that will give rise to reactive alumina and system, and this was actually discovered long back. So, Romans used this for their viaduct and things like that, and that is why the name pozzolana came into being. So, reacts with lime, this reacts with lime because it is reactive. So, same reaction as I was just mentioning, this one, this one lime, some active clay reacts. So, basically what is happening is your calcium hydroxide reacting with some sort of silica, forming calcium silicate hydrate sort of thing, or rather if I write it in that form, CH plus S in presence of some water would form CSH. So, that is pozzolanic reaction is something of this kind, it reacts, right. So, this is what has been, so this has been used. So, pozzolana, therefore, fly ash you can use, GGBFS you can use. So, product from thermal power plant collected at electrostatic precipitator, product from thermal power plant collected at electrostatic precipitator, right. Now, you can see that coal when burnt, it is grinded and burnt, grinded to fine powder like powder condition, so that its surface area is large and it can burn now, but the clay as impurity which comes from the mines along with it, that also get heated up, and the fine ash that goes, we call it fly ash. Fine ash that goes towards the chimney along with the flue gases, that we call as fly ash. The larger ones we call bottom ash, they go down below, but this fly ash we cannot leave it to the atmosphere, and they are charged very fine particle colloidal form suspension. When you put it into electrostatic precipitators, they are collected as powders. So, this is then reactive clay, same reactive material, reactive silica and alumina, because we have heated it up and then cooled it very rapidly, something like volcanic ash itself. Similarly, ground granulated blast furnace slag. Now, slag is removed from blast furnace and grinded, and granulated. Now, what is when you are producing iron, so steel production, iron will be, the ore will be molten, you will melt it. Now, it will contain a lot of clay, impurities. How do you remove it? Lime is added to this. So, lime is added to remove clay, to remove impurity, to clay impurity or silica alumina SiO2 system or Al2 system from iron. Now, iron is very heavy, 7.85, molten iron. So, this material lime and this in the hot condition, they actually form a slag and floats over the molten iron. This is drained out, then this is grinded and granulated, and this is also granulated to fine sizes, almost cement sizes, and this is also reactive, because same issue, it is been heated up and then cooled rapidly. Now, this will have lime also. So, this will have lime also, while this may have lime or may not have lime. It will depend upon how much impurity was there in the ash in the form of lime, but in this one lime will definitely be there. So, this is other one. This silica fume comes from as a byproduct from silicon and ferrosilicon industry. What they do? They heat up quartz. Quartz is heated up to high temperature of the order of around 2200 degrees centigrade, and to actually get silicon metal. Now, in the process some silicon oxide, very rich silicon oxide, around 85-90% silicon oxide rich, fumes or gases comes out, which is condensed and you get what is called microsilica or silica fume, condensed silica fume, and this is also a material which will react with calcium hydroxide easily, calcium hydroxide easily. So, this will also react with calcium hydroxide easily. We shall see some of them. Rice husk ash, if you burn anything now which is rich in silica and alumina and form the ash, rest of the material will go out, carbon etc. will go out. So, rice husk, if you burn it, you can actually produce some sort of pozzolana, and we will see quickly some of their reaction. The essential reaction in this pozzolanas are C3, something like calcium, same tricalcium silicate reacting with water, some calcium hydroxide. Now, this calcium hydroxide reacting with silica in presence of water to form CHS, that is the kind of essential reaction in this is called pozzolanic reaction, essential pozzolanic reaction, right. The stoichiometry is not very difficult, around 1.85 calcium hydroxide is required to react with 1 unit of silica to produce 2.85 this product, right. So, we might even look into this again. So, there are various types of pozzolana, fly ash of varieties kind, silica fume, ground granulated blast furnace slag. Now, 2 types of fly ashes has been classified according to STM classification. One is called type F, other is called type C. Type C has got high amount of calcium hydroxide, that is what I was calcium oxide, that is what I was telling you, because the impurity in the carbon or coal system, it contains sufficient lime. Calcium carbonate can be also an impurity. So, when it is 10 to 40%, this is called type C. Type F has got this less, while this is this higher. Obviously, this is less here, rest all somewhat different. So, if you look at it, here this is 80% silica, rest all are very small silica fume. Ground granulated blast furnace slag, you will have this much higher, because you have added lime to remove the impurity out from it. So, therefore, this has got lime, this has got. Now, cement, if you compare, just like for OPC, let me write it here, this will be about 21%, 20% or so, this will be around 65% or so, this is about how much, 8% or something of that order, So, they are small, these are larger ones. So, if you look at this, this has got somewhat less lime, this has also got still lesser limes, and they do not have lime. So, therefore, this one GGBFS can show some sort of cementitious reaction also, because both this is active, this is also active, but they do not exhibit this reaction on their own. You need a catalyst or an activator to start this cementitious reaction in lime, right, cementitious reaction in lime. So, therefore, if you activate them GGBFS, you can make new kind of cement, we will come to that. Now, one more important aspect is the physical characteristic. This is 5 to 150 micron, similar size, particle size micron, and this is very small, 1 to 5 micron. Some more comparison we will have quickly. This is how fly ash is produced, a schematic diagram, right. Coal bunker, this is coal pulverizer, this is crushed fine powder it is made, and then hot air, the hot air, and then this is hot air duct, etc. And then essentially this essentially the burning occurs somewhere here, and then the flue gases go, this is ASP, and electrostatic precipitator collected here. This is to either to a lagoon where they are stored, because this is a waste, fly ash is a waste. So, you will find somewhere there are what they called is ash ponds, right, ash pond, and others could be in a hopper. So, bottom ash goes to the ash pond generally together with some fly ash, but nowadays it is not recommended that fly ash should be sent to the ash pond, because there is not bottom ash and you mix it up, then they are not useful actually. So, if you mix two things up, it is not useful, right. So, this is how it is. So, this is how it is produced actually, this is what is. So, coal, pulverizer, combustor, fly ash, dry process, electrostatic precipitators. if your bottom ash is usually made slurry with water through wet process of transport and sedimentation in the pond it is done. But you see it has got a double effect now. Double effect is, if the wastes are not utilized, you would need space, right? You would need space. So, where to store them? So, if you have visited some thermal power plants, you will find huge ash ponds all around in many places, because good old days, they would actually mix up fly ash and bottom ash together, make a slurry out of it and put it in ash pond. That is not the best way to use them, because they and then what you do, the pond gets all full, you need more land, or you might make a mound out of it, a hill. Then what you do, the hill actually gets, and then hill if you are doing, then you have to have greeneries on top of it, so that it doesn't fly away, stability of this one, there are several issues involved. So, this is a problem, and this is again shown in the similar manner. The flue gas goes here, right, flue gases, precipitators collected, etc., etc. So, raw feed to the silo, oversized pulverized fuel ash, there can be a classifier which can separate out the finer ones from the coarser one, a processed fly ash. So, these are the silos where they can be stored, right. So, this can from the ESP it can go to the, this is the chimney, flue gases go out and through electrostatic precipitator it goes, raw PFA is stored in the bunker, and then one can separate them, classify them, do all sorts of things. So, we shall see that. This can be used in cement. So, we look into other cementitious material, or as we call it, they are classified as cementitious, because they can give cementing property, and we will look into them. We can have some questions from you. Have a small break.